So welcome everybody to this great Chern-Weil Symposium. We're very happy to have Rick Schoen to speak about minimal submanifolds in the Riemannian.
Okay, well, thank you, Carlos. Is the microphone okay? Okay. See if I can get that up. Okay. Okay. Well, it's a pleasure for me to speak in this in the Chern-Weil Symposium. Actually, I've always been indebted to Chern because, excuse me, he hired me in my first postdoctoral position in Berkeley, and when I graduated in 1976. So he was in Berkeley till about 1980. In fact, he was in Chicago, of course, much earlier than that. But he's always been a certainly big inspiration to me. I only met Andre Weil briefly, and I think at the Institute in about 1979. I talked to him a bit, but I was less close to him mathematically. Actually, I'm speaking on a topic which Chern worked on several aspects of. In fact, not really the ones that I'm going to focus on, but he worked quite a bit on minimal submanifolds from the late 60s on. So what I'm going to try to do in this talk is to survey a set of ideas, focusing first on the case of minimal hypersurfaces, where there's a pretty good theory and also currently very active theory, and I want to give some speculations about something that's very largely unknown, which is a similar set of ideas in higher codimension, and I'll talk about just a few results there. And so I'm going to start just in a very general way, talking about volume and mean curvature, and then I'm going to get into existence and regularity or compactness questions, and then I'll bring in some Riemannian geometry in part 3. So it turns out the hypersurface case is very closely related to scalar curvature of Riemannian manifolds, and then I'll talk about higher codimension where slightly different curvature conditions come up. Okay, and so if we have a curve or a submanifold of a Euclidean space or a Riemannian manifold, of course we can measure its length or its area. If it's k-dimensional, we can measure its k-dimensional volume, and then we can ask what happens to the volume when we deform the submanifold. So we think of the submanifold as a configuration that we can move around, and so if you take a vector field on X and you push the submanifold in the direction of the vector field, then you can ask how the volume changes. So assuming everything is smooth, the calculation it's a calculation to see, well, at least if the vector field is normal to the to sigma, that the rate of change of the volume is just minus the inner product of the mean curvature vector with the deformation vector field. That's at t equals 0. So the mean curvature vector is the trace of the second fundamental form. So it measures the average curvature of the submanifold with respect to the ambient manifold. And so that's called the mean curvature, and that's the fundamental object for this talk. And in particular, we see that the volume is stationary. So the stationarity condition is the condition that the mean curvature be 0. And such a submanifold is usually called minimal or sometimes stationary. And so it's important to note that minimal doesn't mean volume minimizing. Typically, minimal submanifolds don't minimize the volume. And so of course, the one-dimensional case of this would be just a geodesic in a Riemannian manifold. Okay, and so the nice thing about minimal surfaces, there are several nice things, but for one thing, it's a very classical subject. They've been studied really for hundreds of years. I think starting with Plateau and then Lagrange developed mathematical ideas around them. But the other nice thing about it is for surfaces in 3 space, they can be parameterized nicely in terms of holomorphic functions, and it's possible to use computers to draw them. And so there are lots and lots of beautiful pictures of minimal surfaces. So this is maybe the simplest non-flat one. Of course, the plane is the simplest, but this is called the catenoid. And so it's a surface of revolution, which has zero mean curvature, and it was studied by Euler in 1744. And it's an example for us of a surface of what's called finite total curvature. So notice the behavior at infinity. Of course, you can't quite see it here, but you can see that the surface is flattening out as you move out. So there's a neck, and then when you go out, the surface looks like a pair of planes, a pair of flat planes. And so, in fact, its total Gauss curvature is finite. And so that's an important class of minimal surfaces for us. A related example turns out to be the helicoid, which was studied by Euler in 1744. And so it's a surface, it's a ruled surface. So you take a straight line and you rotate it as you move up along an axis. So in fact, you sometimes see them as wind devices in a garden, right? So if you hang it out, the wind makes it spin. So that's the helicoid. And so that's another nice minimal surface. There were whole lots of minimal surfaces discovered in the 19th century using complex analytic methods. This is a periodic surface discovered by Schwarz in the 19th century. There's a fundamental piece of it there, and it fits together in space as a triply periodic surface. This is another surface which actually wasn't discovered, losing the bottom there, wasn't discovered until the 80s. Actually, it's also a surface of finite total curvature, but it has 3 ends. There's an upper end, which is sort of catenoidal type, and then there's a middle flat end and then another lower end. It was discovered by Costa in the mid-80s, and it was shown to be embedded. So it was discovered with a formula. It wasn't clear that the surface was actually embedded, but it was shown to be embedded by Hoffman and Meeks in around late 80s, I think. And actually, there are higher genus versions of the surface. So you can, it turns out, add a lot of handles around the center there, and you still have 3 ends, but now you can make the genus very, very large. And this is a sort of general construction of Capilleius from 97. So there are lots and lots of examples. And so the classical existence question for minimal surfaces is called the Plateau problem, and it's named after Plateau, who was a physicist in the 19th century. So he did actually, that may be the 18th century. He did extensive observations on the behavior of soap films and bubbles, and so minimal surfaces are the mathematical model of models of soap films if you ignore the mass of the surface. So if you neglect gravity, then soap films satisfy the variational principle that they minimize area for their boundary. And so the Plateau problem was formulated in 1760 by Lagrange, and the problem is to, given any reasonable simple closed curve in R3, to find a surface which bounds gamma and has least area among all such. And so to make it precise, you have to specify the type of surfaces that you allow. So in any variational problem, you have to specify what the competitors are. And so for surfaces, you could ask whether you fix the topology of the surface in some way, or you limit it, or whether you require the surface to be orientable. There are various different formulations of the Plateau problem. Do you allow surfaces that are singular? And so, and in general, even the question of the boundary is an issue. And so, this is a picture of a soap film, which is the one that almost every talk on minimal surfaces has. I think this must be the one that comes up if you Google Plateau problem. So it's a picture of a soap film spanning a wire. It's a relatively simple one. It's not a very complicated wire, and the soap film in this case is a disk type surface. Okay, and so We can also, of course, generalize the plateau problem to higher dimension and codimension. So you could ask the generalized problem is given a k-1 dimensional boundary, submanifold gamma, which bounds a k-dimensional submanifold, to find the least volume submanifold which bounds it. And more generally, you can formulate it for cycles. So there's so a k-cycle is just a closed-oriented submanifold of dimension k, and you can formulate the plateau problem in homology. So two integral cycles are homologous if their difference is a boundary. So there's a k+1 dimensional chain or submanifold whose oriented boundary is the difference between those two. So that's integral homology. And then you can ask, given a k-dimensional homology class, or given a k-cycle sigma naught, can we find a k-cycle homologous to sigma naught of least volume? So that's another direct generalization of the plateau problem. So to visualize that, you can just think of a curve going around the handle of a torus. So you could take any complicated curve and you could shorten it, so it becomes a geodesic in that homology class, or in this case, it's also a homotopy class. Okay, and so the solvability of the problem. So the original theorem in the subject was done around 1930 by Douglas. So he won the first Fields Medal for solving the plateau problem for disk-type surfaces. So he looked at a curve, a Jordan curve in Rn, quite a general sort of curve, and he showed that it's possible to construct a least area disk which spans the curve. And actually, the work was generalized to Riemannian manifolds by Mori in 1948. Now, a framework for the generalized plateau problem, so in higher dimension and codimension, was really developed much later. It was only around 1960. Well, actually, there are different formulations, but I think the most successful one is the theory of integral currents by Federer and Fleming. And so in this case, the minimizer is constructed as a limit of a minimizing sequence. And so taking that limit requires completing the class of smooth-oriented submanifolds in a natural topology. So you need to be able to take limits of submanifolds only knowing that their volume is bounded. So actually, in a certain way, Douglas's solution also had that. It was a variational construction. However, in the general case, there's a much more complicated issue, which is that the limiting, that when you do the closure of submanifolds, you have to introduce lots and lots of complicated singularities. And so it's possible that the minimizer that you get, you produce a minimizer, but the price is that the solution could be potentially very singular. And in some cases, it will be singular, of course. It may not be a smooth submanifold. Okay, and so so the solution and also the proofs of regularity for the plateau problem really were a very important motivation for lots and lots of techniques, both in geometric problems and also in PDE, in partial differential equations. The ideas of partial regularity are also really important, been used a lot. And so I should say there are many cases where singularities can't be avoided, such as a complex variety in Cn is always a solution of the plateau problem for its boundary. So in those cases, you definitely do get singularities. Those are higher codimension. I'm going to talk about that later in the talk. But in the codimension 1 case, it was assumed, I think, that the solutions, the minimizers, would always be regular. And so it was a really big surprise in the subject in the late 60s when it was discovered that that's not really true. So through the work of several people in the 1960s, when the dimension is large, 8 or more, it can happen that a volume minimizing hypersurface, oriented hypersurface, is singular. And so this was discovered through the work of many people. And on the geometric side, Jim Simons wrote a really important paper in the area. Okay, and so you can ask, I want to just bring up this topic because there's been interesting progress recently. So you can ask, well, there's no topological reason for singularities to be there for hypersurfaces. You can always fill in with smooth submanifolds. So the question is, why are they there? Are they there for any reason? And that's really a largely unsolved question. But you can ask maybe a simpler question as to whether they're stable. In other words, if you perturb the boundary, say, do the singularities always persist? The singularities in the interior. And it turns out there's some interesting progress. The answer to that is not known fully either. But, or you could ask if you do it in homology, if you fix a codimension 1 homology class, can you deform the ambient metric so that the representative, a minimizing representative of that class is regular? Okay? And so it turns out that back in the 80s, there was work done on this by Nat Smale. He actually, it extended work of Hart and Simon from Euclidean space, and he proved that in fact, in the lowest dimensional case, where the singularities are isolated, they are unstable in the sense you can always perturb the ambient metric to make them go away. And very recently, this generic regularity result was extended up to dimension 10. So it was done by Chodosh, Montelides, and Schulze. And it's still not known in general, but it would be really interesting to know whether the singularities actually disappear when you perturb the data, either the ambient metric or the boundary, if you were doing the plateau problem. So that's a topic. This is just over the last few years this was done. Okay, and so let me just say on the regularity side, so this is going to be a very general talk, so I'm not going to get into details of things, but it turns out that the regularity of minimizing hypersurfaces depends heavily on the minimizing property. Okay, so if you look at, you can sort of see that from the examples I gave, right? Because those examples were non-trivial surfaces in R3. So for example, the catenoid, if I scaled the catenoid down, it's still a minimal surface, but it converges to a pair of planes with a little neck. There's a singular point there in the limit. And so the catenoid you see is a minimal surface, but it's not minimizing. Okay, that's the key thing. And so the regularity results really strongly use the minimizing property. So in the stationary case, if you just consider stationary singular surfaces, there's almost no regularity known. It's not even known if an isolated singularity is removable in R3. So you could have a surface which is perfectly smooth, bounded area, and everything near the origin. Whether it extends as a smooth surface is unsolved. It's minimal. But there's an intermediate class of hypersurfaces which are between the stationary case and the minimizing case, which are called stable. So those are surfaces that are that are stationary and which have non-negative second variation of volume. So in other words, they're local minima, if you like. And it turns out that that there is a regularity theory for stable surfaces. And the theory in low dimensions was developed. So it's really not a regularity theory, it's really an estimate, a priori estimates. And so in low dimensions, Simon, Yao, and I developed that, and Simon and I extended the result to all dimensions, which of course in higher dimensions you do allow singularities. And the theory plays an essential role in the regularity of min-max hypersurfaces. And I should say also the work of Simon and myself was extended in an important way by Nishan Wickrama-Sakara also. And so, so there's another sort of set of existence theorems for minimal submanifolds which are min-max constructions, right? So you in general don't expect to have minima, but you might hope that you can construct a saddle point. So you you might be able to construct a critical point by doing a min-max. So for example, in the way that the equator of the two-sphere is constructed by sweeping out the two-sphere by circles. Right? You take a maximum for each sweep out and then you minimize over the sweep outs. And actually this min-max theory was developed originally a long time ago. In fact, actually Almgren developed min-max theory in his thesis, which is in the 60s. So it was done in the geometric measure theory setting, and he was able to construct stationary varifolds, integral varifolds of any dimension in Riemannian manifolds using it. But more recently, there's been a resurgence in this area, and in particular, there's a lot of really interesting extensions and applications of it, especially due to Marquez and Andre Neves here. And so I'm going to discuss some of the analytic underpinnings of it. And so, as I said, the work of Almgren gave a construction of min-max solutions which are quite singular, so they're what are called stationary varifolds. So they can have a lot more singularities than than I've been discussing. Later on, a student of John Pitts, who's was around my time in the late 70s, developed a method to prove regularity of these things in the codimension 1 case, and he developed this idea of almost minimizing. And ultimately, the regularity statement reduced to the following limiting question. So you can ask, well, we don't necessarily have to prove regularity of this singular thing. We can, what Pitt showed is that you can construct the min-max surface locally as a limit of smooth, embedded, stable surfaces. So smooth, stable hypersurfaces with bounded volume and, say, properly embedded in a ball. So you can ask the question, if I have a sequence of smooth, stable things, then is the limit necessarily smooth? And so that's another kind of regularity question. And that turns out to be exactly the thing that we had done in the stable case. And so for n less than or equal to 7, the sequence will in fact have uniformly bounded curvature. And so any such sequence, so the curvature being bounded means the tangent planes are well controlled, so the limit will be really in a smooth sense. In the higher dimensional case, the limit will be smooth away from a small set, a set of dimension at most n minus 8. And so you get that kind of picture. And in particular, it resolves in the positive this limiting statement, and it then shows that, at least in codimension 1, these min-max hypersurfaces are actually nice smooth objects in low enough dimensions, and they have small singular sets in higher dimensions. So that's a basic result about the Almgren-Pitts min-max. Now, a closely related question concerns what are called Bernstein-type theorems. So one of the basic principles in geometric problems often is that you can have this very complicated thing locally, but when you rescale it, when you take a limit, it simplifies a lot. So you probably heard of tangent cones for minimal submanifolds. That's an example of that. But more generally, you expect some sort of rigidity statement for the non-compact case, which is thought of as the blow-up of a singular guy or a limit blow-up of a sequence with high curvature. And this kind of rigidity statement for complete solutions, often called Bernstein-type theorems. And because Bernstein proved such a theorem for entire minimal graphs in 1915. It's the first result of that type. Okay, and so if you have a non-flat minimal hypersurface or minimal submanifold of any dimension, you can always scale it down, and when you do that, the curvatures are going to get very large, right? When you scale down, the curvatures blow up, and so the possibility of curvatures blowing up is very much related to whether there exists complete non-compact, complete complete submanifolds of that type, and so conversely, there's a converse to that. You can also show if you had a sequence where the curvatures are blowing up, you could rescale it and produce in the limit. At least in many cases, you could produce such a counterexample to a Bernstein theorem. That would be the idea. And so when you ask the question for minimizing hypersurfaces, that's equivalent to the regularity question. So the Bernstein theorem is true for minimizers up to dimension 7 and false for n greater than or equal to 8. So one of the things we did is prove the Bernstein theorem for stable surfaces. So we assumed Euclidean volume growth. So the volume in large ball as at most r to the dimension. And recently, actually a long time ago, I had removed the volume growth assumption in the two-dimensional case. So that's a special case. And actually, it was also done independently by Pogorelov. But in recent years, just over the last few years, there's been more work on this. There are several authors, Otis Chodosh, Chao Li, Laurent Mazet, Paul Minter, and Doug Stryker, who removed the volume growth assumption for n up to 6. So notice that's one dimension short of the optimal result for minimizers, and that 7-dimensional case is still not known. But there is some another interesting work by Bellatini, which removes the embeddedness assumption for n equals 7. Actually extends the theory that Simon and I had to higher dimensions in a nice way also for immersions. He gives a different proof of that result. Okay, and so I want to now bring in, do I have an hour, by the way?
Yes.
Okay. Okay, so I want to now bring in Riemannian geometry because it's also very closely related to the stability theory. And so, so generally in Riemannian geometry, of course, the curvature of the ambient manifold, so there's a picture of a sphere there, it affects the stability or instability of geodesics, or you expect a similar thing for minimal submanifolds, although that's generally quite hard. So for example, the equator on the sphere, if you push it just parallel in one direction, while the length is stationary, the first derivative is 0, the second derivative is actually negative, and the length decreases. Okay, and so generally positive curvature is having the effect of decreasing, of being able to deform submanifolds so that the volume is tending to decrease. Okay, and so the way that things like that are done is through the second variation, and so I've written it down here. So so if you study, so we saw that the first variation being 0 means minimality, and the second variation involves a formula. So if you look at a variation vector field X, as we did before, in the hypersurface case, there's a very special thing that happens in that the normal bundle is one-dimensional. So you can write X as a function times an everywhere defined unit normal. So assuming the hypersurface is two-sided, and then there's a calculation which says that if assuming the first variation 0, the second variation is given by this expression. So, so phi here is an arbitrary function with compact support if there's a boundary. Okay, so this is just the ordinary Dirichlet integral there, and then this is the scalar term. This zero-order term here is depends on the geometry of the submanifold. This is the ambient curvature, the curvature of the ambient manifold. So you can see that if the Ricci curvature is positive, that's tending to reduce the area. And then this A is the second fundamental form. It's the square length of the second fundamental form. So the more curved the surface is, it also tends to make it less stable. It's the basic idea. Okay, and so in particular, you can see from that formula that if you chose the function phi to be 1, and if it were a closed hypersurface, and if the Ricci curvature were positive, then it can't be stable. And so if you combine that with the existence theorem, you would conclude that the n-1 dimensional homology of a manifold of positive Ricci curvature is 0. Okay, well that's a true theorem, but you don't need this heavy machinery to do it. I mean, it's a theorem, it's a classical theorem, maybe due to Bachner in the 40s using harmonic forms or Hodge theory. So there are different ways of approaching that. So it looks like the minimal hypersurface theory is just going to reproduce known results. However, there's another way of writing the second variation, which makes it much more effective. And in particular, you can manipulate that zero-order term that we had. It's a little slow. Yeah, so maybe I didn't go back, but you can manipulate that zero-order term to write it. You can throw away half of the second fundamental form squared and replace the the Ricci curvature term by the difference between the scalar curvatures. These are scalar curvature functions of the ambient manifold minus the submanifold. And so now, if you choose the simple variation phi equals 1, so that corresponds to taking a parallel variation, if you assume the scalar curvature of M is positive, then you deduce from the positivity, so stability would mean this is non-negative, you would come to the conclusion that the total Gauss curvature of the surface is positive. And so from the Gauss-Bonnet theorem in 2 dimensions, that implies the surface is a sphere. Okay? So it's a little different situation. You don't prove that minimal hypersurfaces don't exist, stable minimal hypersurfaces, but you prove that they are, in the 3-dimensional case, they would be topologically a 2-sphere, and indeed that does happen. I mean, so S2 cross S1 is an example of a manifold of positive scalar curvature in 3 dimensions. So there are lots and lots of stable minimal spheres in 2 dimensions. Now, in higher dimensions, there's an argument. So this is work of mine and Yao going way back. There's what I'll call slicing stable hypersurfaces. So the 2-dimensional case, the case we discussed, suggests that if the ambient manifold has positive scalar curvature, then in a certain sense, the stable surface also does have positive scalar curvature. And so one can make that precise in arbitrary dimensions. So the basic philosophy is that you start with positive scalar curvature. That property is inherited by stable hypersurfaces. Okay, and so this suggests the idea of considering slicing. So you start with some high-dimensional manifold, and then you can consecutively slice. And each of these, assuming you can do the relevant minimization, each of those hypersurfaces would have positive scalar curvature. And so, in particular, we could start in n dimensions, and if we can do this slicing, when we get down to 2 dimensions, we'll have a sphere. Okay, and this idea, this slicing idea, actually can be used to do lots of things for positive scalar curvature, such as showing a torus cannot have such a metric, and things of that type. So this is a direct connection between stable hypersurfaces and positive scalar curvature. In fact, actually, this idea that stable hypersurfaces tend to have positive scalar curvature is really the motivation for some of the Bernstein theorems I mentioned too, the recent ones which remove the volume assumptions. Okay, and so how am I doing here? Oh, I'm going quickly. Okay, so let me now go to higher codimension. Okay, and so so first of all, the existence and the regularity for minimizers actually work in arbitrary codimensions. It's at least for integral currents or for oriented submanifolds. And so in general, a volume minimizer would be regular away from a closed singular set of Hausdorff dimension k minus 2. K is the dimension of the submanifold, and you see that that's sharp so a complex variety generally has codimension 2 singularities, and this theorem was, when I was growing up in the subject, was sort of the massive paper of Almgren, which was developing from about 1980 till 1990 almost, I think, and it was published eventually as a 1,700 page article, but it's been worked over more recently. It's a really hard theorem. It's a deep result of Almgren. It's reworked and simplified by Camillo Dalelas and Spadaro. So they rewrote Almgren's work, and the main result again is the regularity away from a set of codimension 2, Hausdorff codimension 2 for volume minimizers. Okay, now if you ask a similar question for stable submanifolds, it so far has no satisfactory analog in higher dimensions. The second variation of the volume looks pretty similar to the codimension 1 case, so I've written it here. So the difference is that V here is a normal vector field. So instead of being given as a function times the normal, it's actually a system, right? has values in a higher dimensional higher dimensional space. It's sections of the normal bundle. But this is again a Dirichlet type integral, but the derivative, of course, depends on the geometry of the normal bundle. So the normal bundle has a connection which is induced from the ambient manifold, and this is del perp. That connection is not an ordinary type Dirichlet integral. And then the zero order term again is pretty similar to the one before. This is the second fundamental form, but now in higher codimension, the second fundamental form can be computed in any given normal direction to get it's vector valued, and so this is the second fundamental form in the v direction. It's the norm squared, and this is again an ambient curvature term, and it's and so these are this is a sort of partial Ricci term. It's a so each of these. So if the sectional curvatures of the manifold were positive, say, then this would be a positive term, which would again tend to make it unstable. Okay, and so when the dimension is 1 or n minus 1, the normal bundle is flat, and you can always find local normal vector fields that are parallel. Whereas in higher codimension or higher dimension and codimension, that is not possible. And so that first term that we have written there is very hard to control, this term. So you can't, so I couldn't choose phi equals 1 to make it 0 or something like that. Was the simplest choice I made before. There's just no such analogous choice. And so as a result, there's just very little known about the existence of stable submanifolds in higher codimension. However, there is a special case where there's been some very useful developments and where there's a possible general theory, I think, and that is the case when k is 2. So if the submanifold is two-dimensional and the ambient manifold is higher dimensional, then you can use complex analysis. So the surface is, if you assume, is orientable, and then of course it has a metric in orientation, so those define a complex structure on the surface. And then there's a natural way of complexifying the second variation. So you can consider, initially we considered real variations, but you can just complexify everything and consider complex variations, so they just consist of a pair of real variations. And then you can get rid of that first term, which was the full Dirichlet integral, and replace it by just the z bar derivative, where you differentiate only in the z bar direction. Of course, in order to do that, you have to do a couple of integration by parts. Those integration by parts change that zero order term, and what you get is there's a factor of 4 there. This is the z bar derivative squared, and then this term is, so this is again a second fundamental form term, and this term here is a complex sectional curvature. So dz is the 1, 0 tangent vector, and v is a complex valued vector. So you think of complexifying, extending the Riemann curvature tensor complex linearly, and then you can make sense of complex sectional curvatures. Okay, and that's what this is. It's a complex sectional curvature in the complex plane spanned by dz and v, and the bars over the last two make this a real quantity. So you can extend sectional curvatures to complex sectional curvatures, and in fact they come up in various settings. Oops. Not sure what my okay. Right. And so there's a complex version now. Now the advantage of this version of the second variation is that while in the original second variation formula, this first term we really had no idea how to make. We couldn't make it 0 even locally, right? But for in the complex version, you see that if you choose v to be holomorphic, or almost holomorphic. I mean, the point is that while the full gradient is a very much overdetermined quantity, overdetermined quantity. You can't make it zero or even, say very much about it. When you replace it by the z-bar derivative, you at least locally can construct holomorphic solutions. You can expect to be able to control that first term in a more effective way. And so it turns out in 2 dimensions, this is a way of a rewriting of the second variation, which turns out to be really useful. And so let me mention two old applications of it, and then I'll talk about possibilities for sort of a more general theory. So first of all, there's the existence theory. So it turns out the work of Sachs and Uhlenbeck from about 1980 constructed minimizers for minimal two-spheres. So if you look at the special case of a two-sphere in a Riemannian manifold, then you can ask, can I minimize the area in a homology or even a homotopy class? And Sachs and Uhlenbeck developed not only minimization but also min-max theory for that problem. And that work was applied in 2 interesting ways. One by Su and Yao, who showed that stable two-spheres in Kähler manifolds with a certain curvature condition, positive bisectional, are either holomorphic or anti-holomorphic. And they used a slightly different, they looked at it in a slightly different way, but it's equivalent to this complexified second variation. And so it was a step in their proof of the classification of manifolds like that, so-called Frankel conjecture. And then a few years later, McAuliffe and Moore did a very interesting thing. They used the min-max theory, that is the variational theory, two spheres to show that simply connected compact manifolds with a certain positivity condition, positive isotropic curvature, are actually homeomorphic to Sn. And it was really the first sphere theorem for pointwise quarter-pinched manifolds. That was done in the late 80s. So it's another beautiful application of the higher codimension minimal theory, but only for S2s. And so both of these works exploit the special structure of holomorphic vector bundles over the two-sphere. So a holomorphic vector bundle over the two-sphere has a very special property in that it splits as a sum of line bundles, and then you can understand exactly when those line bundles have holomorphic sections. And so both of the theorems use that idea. And so one of the things I've always wanted to do, and we made a little progress on this recently with Fraser, is we extended some of the stability results to higher genus surfaces. And in particular, I'll tell you about a couple of them for the torus. And I think there's a good hope of doing it, of improving the theory quite a lot. But before, so let me tell you about one of the theorems to begin with. So the basic picture here is that stable hypersurfaces are to positive scalar curvature as stable surfaces, two-dimensional surfaces, are to positive isotropic curvature. Okay, so the corresponding positivity condition that comes out of the second variation really is positive isotropic curvature. Now, I just explain it a little bit here. So I mentioned the complex sectional curvatures. So what McAuliffe and Moore realized is that you really don't need all of the complex sectional curvatures. You can, in many cases, require that the complex plane spanned by x and y is isotropic. So see the normal bundle, the complexified normal bundle has an underlying real structure, and so you can extend the inner product either as a Hermitian product or as a complex linear product. If you do the complex linear one and you require VV to be 0, that's called isotropic. So it just means that the real and the imaginary part are orthogonal and of equal length. That's the condition. Okay, and so it turns out that for many applications it's sufficient to consider that, and it's a much weaker curvature condition than positive complex sectional. Okay, and so what you can then formalize that, you can look at the isotropic curvature being bounded below by a positive constant, so kappa positive. So McAuliffe and Moore showed that, that any manifold of positive isotropic curvature, if it's simply connected, then it's actually homeomorphic to a sphere. That was their main theorem. And so we proved a sort of local version of that for the non-simply connected case. And so it turns out manifolds of positive isotropic curvature can have very large fundamental groups. They can have fundamental groups that are free groups, for example. And so if it's not simply connected, and if we think of a subgroup of the fundamental group of M, then we can define the systole of that subgroup, cis of G, which is the shortest geodesic, which is freely homotopic to a non-trivial element of G. Okay, and the systole of the whole manifold is the systole of pi 1. And so a kappa pick manifold can have very large systole. I mean, for example, I can take a sphere and I can cross it with a very long circle, and then the only non-trivial element in pi 1 is the circle, and I can make that as big as I want. So, and that is kappa positive, you know, kappa pick for, I can make it any kappa by taking the sphere to be of large curvature. Okay, and so the result we proved is that if you take a kappa pick manifold, and if you take a subgroup G, which is a non-cyclic abelian subgroup of pi 1, then the systole of that subgroup is bounded by a universal constant over the square root of kappa. So it's a kind of, if you study Riemannian geometry, you know Meyer's theorem, which says that if the Ricci curvature is bounded below by kappa or n minus 1 kappa, then the longest stable geodesic is bounded in length by pi over square root kappa, right? So this is kind of in that spirit, and the constant is very effective. It's, we don't know that it's sharp, but it's, so the constant for most dimensions is 2 pi over 3, and there are a couple of cases, 5 and 6, where we have to increase the constant a little bit. And so this is a result that uses the stability in this case for, so I'll just outline the proof here, uses the stability in particular in this case. We can realize G for a non-cyclic abelian subgroup, a fundamental group. We can realize it by a torus, a least area immersed torus or branched immersed torus, and then that's then stable. And so we can then look at that minimizer, and then the systole of the surface is then at least as large as that of G, because if I take a closed geodesic on the surface, then that will in general have length bigger than the corresponding freely homotopic geodesic in the manifold. So it suffices to give an upper bound on the systole of the stable torus. And so the way we do that, okay, and so I'll say just a little more about this at the end, but the idea, so the stability inequality with kappa pick gives us this inequality. So it tells us for any complex section of the normal bundle, we get this kind of eigenvalue inequality. So it's saying that a certain operator has eigenvalue bounded below by kappa. And the idea is that, well, if the surface is sort of large, then you might expect that you could find an S which is almost parallel or almost holomorphic in this case, and violate that inequality. And in fact, it is possible to do that, but the proof uses some rather non-trivial work. It uses the classification of holomorphic bundles over a torus, which was done by Atiyah a long time ago. So it uses some work on holomorphic vector bundles. Okay, but we're able to do that effectively, and while we don't necessarily get holomorphic sections, we can get almost holomorphic ones. So we just have to make the right-hand side small enough to violate this inequality. So that's the one result. And I should say I didn't talk about it, there are results that are quite analogous for scalar curvature. So there are results that if the scalar curvature is large, then let's say in 3 dimensions, then a stable minimal surface will have small diameter. It will be, in that case, it's the relevant thing is the diameter. Okay, and so let me just speculate a little bit about min-max questions in higher codimension. Okay, so remember our limiting theorem. So the theorem that gave us the regularity, the min-max, via the ideas of Almgren-Pitts, was the idea that if we take a limit, a weak limit of stable, or sufficiently smooth, stable submanifolds, then that limit would also be stable. And we assume the volume is bounded and they're proper in a ball. Then, of course, it could have multiplicity. So it does happen that the limit sometimes is multiplicity, but it still has an underlying smooth, stable surface. Okay, and so there's a very big difference in this theorem. So it is a possible theorem. It could be true. I mean, I think it must be very hard in general dimension and codimension. But a major difference is that even in the 2-dimensional case, if you just consider, I mean, the statement is true for holomorphic curves, say in C2 or in Cn, but it's quite different from the hypersurface case in that while the limit is in fact a smooth submanifold, the convergence is not good. It may not be good anywhere. You can easily construct examples of holomorphic curves which converge to a multiplicity 2 disk where the curvature blows up everywhere. So you can just do something like w squared equals epsilon times a polynomial in z in 2 complex variables. You can easily get examples where of course the theorem is true, the limit is still holomorphic, but the convergence is bad everywhere. That's the thing. Whereas in the hypersurface case that was not true. So remember we were able to show that in the hypersurface case, in low dimensions, you actually get smooth convergence. Whereas in high dimensions, you don't get everywhere smooth convergence, but away from that singular set, you do, right? And so that's one very big difference between, and so notice that the regularity theory for minimizers guarantees the theorem is true for minimizers, because a weak limit of minimizers is still a minimizer and is therefore regular. It's just that the convergence is horrible. Okay, and so then I then in the circle of ideas for hypersurface I discussed the blow-up question, the Bernstein type question. So it's quite unclear what sort of Bernstein theorem you could expect. I mean, it certainly wouldn't be true that the complete minimizing or stable submanifolds are flat planes. But, and so it's really hard to even formulate a conjecture in general. But in the 2-dimensional case, there is actually a natural conjecture. And it's, again, based on this connection between stability and the complex structure of the surface and the ambient manifold. Namely, the conjecture, you might conjecture that the blow-ups of these surfaces, which would be stable surfaces, even having minimizing properties, that they're actually holomorphic. So they blow up to complete surfaces that are holomorphic for an orthogonal complex structure on the ambient Euclidean space. So they would lie in an even dimensional subspace, and they would be holomorphic. So the basic philosophy of that would then be that in regions where the curvature is large, which is the ones we care about, the sequence is looking more and more holomorphic. Okay? And so in the holomorphic case, of course, we have the theorem, and so that would be the hope. And so there is a reasonable Bernstein type conjecture in higher dimensions. And while we're not able to do that in general, so let me say that using the same set of ideas I described for 2 spheres, McAuliffe in his thesis, in fact, proved such a Bernstein theorem in all dimensions for the genus 0 case. So if you take a minimal surface of genus 0, it has to have finite total curvature. So you need the condition that the planes converge tangent planes converge at infinity, but he did prove that a stable genus zero surface of finite total curvature in any dimension is holomorphic. Okay, and so we looked at the higher genus version, and we found that it's difficult to, well, the McAuliffe's theorem is not generally true, but it is true in 4 dimensions. So also in his thesis in 4 dimensions, he proved that for without any restriction. Right? And so, we refined the notion of stability a bit. So we have to justify this notion. I'll describe it in a bit, but we called it covering stability. Okay, and so the definition is that the surface is not only stable, but each of its finite coverings, which is trivial outside a compact subset, is also stable. So for example, if S were a surface with boundary, then we would not unwind the boundary curves. We only consider coverings that sort of are non-trivial in the interior of the surface. And so in general, if we take a covering of a stable submanifold, it's not necessarily stable. So the simplest example would be something like a closed geodesic in the real projective plane. It's double covered by an equator on the sphere, and while the geodesic downstairs is stable, the one upstairs is not stable. Okay? And so let me just make a few remarks on it. So generally, if I take an integral homology class and I define a norm, which is the least volume of any representative submanifold or integral current, you can then see just from comparison arguments that if I multiply the class by an integer m, then I have competitors in the class which are just m times the competitors in the original class, right? And so in particular, it's true that the norm is less than or equal to m times the norm of alpha, because I get competitors of that size. And it could be less in general. So equality holding would mean that a minimizing representative would also be stable in this covering sense. And so let me give some examples. So of course the simplest example is the simply connected case. So stability then of course is equivalent to covering stabilities, and there are no coverings. And also the hypersurface case, which I mentioned earlier, the covering stability is also automatic in that case. So if I take a two-sided minimal hypersurface, it is covering stable. So the reason for that is that the Jacobi operator is a scalar operator. So it's because the normal bundle is one-dimensional. So using properties of sort of maximum principle positivity properties of solutions of our eigenfunctions for the a scalar operator, it is actually true that stable hypersurfaces automatically have this covering stability property. A third case, which is of course very important for us, is the calibrated case. So that's an example. So that's, for example, the complex submanifold case, which is we're hoping to come into play here. And so generally, if in any dimension or codimension, if S is calibrated, then it's also covering stable, simply because I can lift the calibration. So if I take a covering, then it's also calibrated. Okay, and so we were able to prove a Bernstein theorem of this type in this covering stable setting. And so the result is, so this is in the genus 1 case again, using the Atiyah theory I mentioned. If it's covering stable, then it lies in, so finite total curvature, it lies in an even dimensional affine subspace and is J holomorphic. So again, that uses, so the assumptions tell you that there's a compactification, which is a Riemann surface of genus 1, and the surface can be parameterized conformally outside a finite number of points, which are the points at infinity. And then we're able to, again, to use the theory of holomorphic vector bundles to do that over the torus. And so that's at least a little bit of progress in this direction. I think it's a very interesting circle of ideas, which, you know, it's quite seem quite difficult in higher codimension, but maybe it's just missing the right idea. So let me stop there.
work for genus 1? You invoke a friendly work on
Yeah, so of course, in genus 1, in general, if you take a holomorphic vector bundle, it doesn't have a section, right? But so what happens is so on the other hand, if C1 is positive, then it will have a section. So these bundles with C1 equals 0, although they don't have sections, they have the property that if you enlarge the torus, so for example, think of a line bundle on the torus, right? So in general, a line bundle doesn't have a section. It really, it's parameterized by a point on the torus. But if you take a big covering of the torus, you can make that almost rational. So you know that the vector that you get, and so you can make it almost trivial in a covering. And so the idea is to by taking coverings, you get not holomorphic sections, but sections that are epsilon almost holomorphic. And so you have to then, it's quite a tricky argument, really. You then have to do that. You have to play the covering off against the epsilon, and you end up proving that that it's holomorphic. And so the thing is, like a line bundle can be very far from being trivial on the base, but when if you're allowed to take a covering, you can make it almost trivial. So that's why we need this covering stability argument condition. Yeah.
And, you have a conjecture for what the Bernstein theorem would be for a stable three-dimensional minimal surface in R5.
Stable three? No. Well, yeah, as I said, the general dimension and codimension is tricky. There is, so you can ask the question, well, 2 dimensions is special for minimal submanifolds, so we sort of understand why. But codimension 2 could also be special, right? I mean, there are some, so there is a sort of Ginzburg-Landau approach to constructing, to actually proving theorems like Almgren's theorem, which uses maps into, so it uses they're complex valued maps, so you get a codimension 2 submanifold. So somehow, two-dimensional surfaces correspond to maps from a 2 surface into a big manifold. Codimension 2 surfaces correspond to level sets of a map from a big manifold into the complex plane. And so, but I wouldn't I wouldn't dare conjecture. I asked this question to Guido De Philippis because he was talking a little bit about this, and well, he's a very optimistic guy, but he didn't really have any concrete. Thank you very much. Okay.